In today's lesson, we are going to look at square roots and cube roots. In the previous lesson, we learned and discussed what a perfect square and a perfect cube is. And so I've listed my first 10 perfect squares here, right? 1 is the first, 1 times 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, and so on. And I've listed the first 10, but this, of course, continues on infinitely. As we look at this, we can define a square root to mean to extract one of two equal roots. So if we can break a number down into two equal roots, like 36 can be broken down into 6 times 6, if we just take one of those equal factors, that is called taking the square root of a number. Okay, so the square root of 25, since 25 can be written as a product of two equal factors, the square root is, it's kind of like an operation, right? So if you multiply by something, you change, right? If I have 5 and I double it, it becomes 10. If I have 25 and I take the square root of it, it becomes 5. It becomes one of those two equal roots, right? So by putting the square root over a number, we are applying an operation to the number. We are telling to do something. So the square root of 49 tells me to take one of two equal roots. Well, the two equal roots are 7, so one of those is 7. So when you apply the operation, you no longer write the operation. You just write 7. Same thing here. Once you multiply by 2, you just write what the number becomes, and you do not write the operation anymore because you have applied the operation to your number. All right, so let's practice taking some square roots. So find the square root of 81. Well, the square root of 81 is 9 because 9 times 9 is 81. The square root of 900 is 30 because 30 times 30 is 900. Square root of 49 we discussed is 7. What happens when you have a fraction? Well, when you multiply fractions, like something like a half times a half, right? If you take two numbers that are exactly the same and you multiply them, you would just multiply the numerators and multiply the denominators. So in other words, if you take the square root of the numerator and the square root of the denominator, you can find the square root of a fraction. So the square root of 64 over 121, well, we know that the square root, that 64 is 8 times 8, and 121 is 11 times 11, so the square root is 8 over 11. 1, the square root of 1 is just 1, because 1 times 1 is 1. Same thing with 0. The square root of 0 is simply just 0, because 0 times 0 is 0. 0.04. Well, if you have two decimal places, a single decimal place multiplied by a single decimal place gives you two decimal places. So if you have an even number of decimal places, you can take the square root of it. The square root of 0.04 is 0.2. Not 0.2, because a 0.2 times a 0.2 would give you two decimal places, and two decimal places would give you 4 decimal places. So be careful with the decimals. Can I take the square root of a negative? This one's a tricky one, right? Because can I make two numbers exactly the same to get a negative? Well, no, a negative times a negative is a positive, and a positive times a positive is a positive, so it's impossible to make them the same and get a negative. So we say this is not a real number. Okay, so you cannot take the square root of a negative. If I put the negative outside the square root sign, this means I am taking away root 25, or I am taking away 5, right? The negative on the outside is okay, right? Or I could put a negative 1 there and say I'm taking the negative of root 25, which is negative 5. But if it's underneath the root sign, you cannot take the square root of a negative. All right, so I know 36 is 6 times 6, and if I have 4 zeros, well, I know when I multiply powers of 10, like 100 times 100, 2 zeros multiplied by 2 zeros gives me 4 zeros, right? 1 0 multiplied by 1 0 gives me 2 zeros. So if I have an even number of zeros, I can just split them up evenly, right? 600 times 600 is 3,600. Therefore, the square root of 3,600 is 600. So we can take the square roots of numbers without using calculators if we are working with perfect squares. Right? If we're not working with perfect squares, we have to estimate or use a calculator. For example, let's put our square roots of our perfect squares on a number line. It looks like the square root of 100 is way bigger than the square root of 81. But really, the square root of 81, isn't that just 9? Right? And the square root of 100, isn't that just 10? And the square root of 64 is 8. So really, all of these, they look like, for example, it looks like I'm getting way bigger because 36 is way bigger than 25, but the square root function tells you that when you take the square root, you just get 6. So really, all of these are just one greater than the next, right? So really, this is our number line from 1 to 10. That's all it is, right? 6, 5, 4, 3, 2, 1. And I can put these right in their appropriate spots. Root 9, root 16, root 25, and so on. I could fill all that in. So if I asked us to estimate, for example, something like, I don't know, root 12, well, I know it's bigger than root 9, and root 9 is 3, right? It's bigger than 3, and it's also smaller than root 16. Root 16 is 4. So I know that root 12 is going to equal 3 point something. And this is where it gets a little tricky. How do I know if it's 3.1, 3.9? Well, root 12 is 3 more than 9, right? Sorry, I should just say that 12 is 3 more than 9, not the root. The 12 is 3 more than 9, and the 12 is 4 less than 16. So the number under the root sign I'm just looking at, which we call the radicand. So this is slightly less than halfway. So I don't know, maybe 3.45 or 3.4. Again, it's just an estimate. You would then go to your calculator and you check to see if you were correct. So you figure out what two numbers it's between, and then you figure out the proportional distance the 12 is related to the 9 and the 16. If it's really close to the 16, like root 15, I would probably say 3.9. Root 10, I'd probably say 3.1. And I just figure out kind of where it falls. So let's practice a couple. Root 20. Well, I know root 20 falls between, well, it falls between root 25 is 5 and root 16 is 4. So I know root 20 is going to be 4 point something. Well, 20 is 4 more than that and 5 less. So yeah, maybe about the same, just a little less than halfway, right? Root 38 falls between 6, right? And the next one up is root 49, which is 7. And 38 is really close to 36, but really far, right? The 38 is really far from the 49. So I'd probably estimate to be closer to the 6, so maybe 6.1-ish, right? So these are just estimates that you can then check with your calculator. It's a good idea to be able to estimate so you can check when you're doing your work if an answer is reasonable. Identify a whole number with a square root between 6 and 7. Well, I know the square root of 36 is 6, so I know the square root of 37 has to be greater than 6. The square root of 38 has to be greater than 6, and I would say ... The square root of 49, let's leave a space there. The square root of 49 is 7. So I know that the square root of 48 has to be less than 7. So all of these numbers, 37, 38, 39, 40, all the way ... to 48. All of those numbers have square roots that are bigger than 6 and less than 49, right? Or less than 7, I should say. Bigger than 6 and less than 7 if you take the square root of them. And so we could count how many there are and see that. If you wanted to know how many there are, you could also take, well, 48, subtract the 36 numbers in front of 37, so 48 subtract 36. We could also figure it out. Oh, there are 12 numbers, right? Because we want 37, 38, 39, so we'd have to, if we had our counting numbers all the way to 36, if we get rid of 1 to 36, we're left with how many we have, right? What about between 10 and 11? Pause the video if you want, give that a try. Then when you've given it a try, you can come back, unpause it, and see if you've gotten the same answer as I do. All right, so between 10 and 11, well, I know the square root of 100 is 10, so the square root of 101 is bigger, dot, dot, dot. I know that the square root of 121 is 11, so the square root of 120 is less than 11, so I'm going to have 101, 102, all the way to 120. All of those are possible options. So if I just ask for any number, just a single number, any of those numbers would be correct. You'd have 20 different numbers to choose from, right? Or in other words, you can go 120, subtract the 100 numbers that come before. There are 20 possible numbers that you could have chosen. And those are the chosen values that have square roots between 10 and 11. If I give you the perimeter, the square area, if I give you the area is 529, then you can use square roots to find the length of each side, right? For example, if I give you the area was 100, you know 100 comes from 10 times 10, right? So the square root of 100 gives you the edge length of my square. So if I have 529, and I'm not sure what two numbers multiply to give 529, but I know it's a square, so they have to be the same. So in other words, I know x times x, or x squared, equals 529. Then if I take the square root of 529, I can figure out that s. And if I don't know what it is, then I can use my calculator, square root 529. So make sure you can find that square root button on your calculator, and when you type it in, you get 23. Right? So now that you know the edge length of the square, you can always find the perimeter by adding up 23 plus 23 plus 23 plus 23, or taking 4 groups of 23, and you would get 500 and, sorry, what did I just do? You would get 4 times 23, I obviously pushed the wrong button, which would get you to 92 meters all the way around. All right, so you can use your square root function to find the edge length. List the first 5 perfect cubes. Well, 1 times 1 times 1 is a perfect cube, 2 times 2 times 2, 3 times 3 times 3, and 4 times 4 times 4, 5 times 5 times 5, and I could keep going on. I'm going to add an extra one, etc. Right? You can see they start getting pretty big pretty fast. 7 times 7 times 7 is going to be big, etc. So these are all perfect cubes because they are created from 3 identical factors. So when you have 3 identical factors creating a perfect cube, we can now find the cube root of a perfect cube. A cubed root means to take one of 3 identical factors. So since we know 125 is a perfect cube, and we know 125 is a perfect cube because it's 5 times 5 times 5, then the cubed root of 125 is 5. So you'll see when I write the cubed root versus the square root, I had to put a little index in there. I had to put a little 3 in there to show me it's a cubed root. The square root, I did not. When there's no number in there, we assume it's a 2. That means square root. But when you have to put a little 3 in there when it's a cubed root, right? So now, without that 3, we would be reading it square root. So it's necessary for a cubed root. All right, so let's practice. Let's place these cubed roots on our number line. All right, well, let's practice a couple other ones. What is the cubed root of 1,000? Well, 1,000 is 10 times 10 times 10. So one of those three is 10, right? So that's taking the cubed root. Once you have applied the operation, you no longer write the cubed root because you've applied the function and it becomes the number after applying the operation. All right, the cubed root of 1 is 1. The cubed root of 8 is 2. So again, these numbers look, cubed root of 216 looks way bigger than the cubed root of 125, but really this is just 6 and this is 5 and this is 4. So when you put them on your number line, they're really your counting numbers, right? From 0 to 6. This is just a number line from 0 to 6. Okay? So if I wanted to estimate, let's say, the cubed root of 30, well, I know it's bigger than 3 because the cubed root of 27 is 3, and I know it's smaller than 4 because the cubed root of 64 is 4. Therefore, it's going to be 3 point something, and since it's pretty darn close to this 3, I'd probably say 3.1. Again, it's just an estimate. You could use your calculator. Good practice is to try find that cubed root button on your calculator. Every calculator is a little different, so see if you can find that cubed root button. If I was to type it in, I'd be getting 3.10723 ... a whole bunch more numbers, okay? And so you can try it on your calculator and see if you actually get that. Let's identify a whole number with a cubed root between 3 and 4. So a whole number with a cubed root between 3 and 4. Well, I know the cubed root of 27 is 3, so therefore the cubed root of 28 is going to be greater than 3, and we are going to go all the way to, and what about 4? 4 is the cubed root of 64, so less than that would be the cubed root of 63. So 28, 29, 30, ... all the way to 63. Any of those numbers, I just said identify a whole number. You could have answered with any of those numbers and you would have been correct. Okay? If I want to know how many there are, you would take your 63 and you would subtract the 27 numbers that become before the 28. So 63 minus the 27 is 36. There are 36 numbers that you could have chosen. If I wanted to know between 5 and 6, well, I know the cubed root of 5 is 125, and the cubed root of 6 is 216. So the possible numbers could have been 126, 127, all the way to 215. How many numbers are there? Well, 215, subtract your first 125 numbers. So 215 subtract 125 is, there are 90 possible different numbers you could have chosen that all fall between 125 and 216. All right, last couple questions. How do I know, given the prime factorization of a number, 3 to the power 4, which means 3 times 3 times 3 times 3 times 5 to the power 2 times 11 is a perfect square? Well, you know a number is a perfect square if you can make two identical factors. So if you have a bunch of factors, prime factors, if you can break them into two identical groups, then it is a perfect square. I have 4 3s, so I can do that. I can put 2 of them in each group. I have 2 5s. Oh, I can do that. I can put 1 in each group. But I only have 1 11. So I can't break that into 2 equal groups. So since there's only 1 11, it is not a perfect square, right? If I put 11 to the power of 2, in other words, if I multiplied this number by 11, it would become a perfect square. Is 5 to the power 3 times 6 to the power 3 a perfect cube? Well, a perfect cube means you can make 3 identical groups. So there's 3 5s, so I can do that. I can put a single 5 in each. There's 6 3s. Oh, that means 6 broken into 3 groups. I can put 2 3s in each, right? 2 and 2 and 2 is 6. So since this is a perfect cube, what we can do is we can take the cubed root of it by taking one of those 3. So we know the cubed root of that is 5 times 3 times 3. That would be the cubed root, or in other words, 15 times 3, which is 45. It was able to take the cubed root of a really big number using its prime factorization.